I wanted, because of the importance of this formula, I wanted to take a couple of minutes out to proof of the formula. Just to give you a chance to stare at a little more. Now, there are 3 proofs I know. I'm sure there are 27. Like the Pythagorean theorem now has several hundred. But there are 3 basic proofs. There is the one I will not give you, I'll call the high school proof, which is the only one normally finds in books, physics textbooks or other textbooks. The high school proofs takes the right-hand side, applies the formula for the cosine of the difference of 2 angles, which it assumes you had in trigonometry, and then converts it into this. It shows you that once you've done that, that A turns out to be C cosine phi, and B, the number B is C sine phi, and therefore it identifies the 2 sides. Now, the thing that's of course correct, and it's the simplest possible argument. The thing that's no good about it is that the direction in which it goes is from here to here. Well, everybody knew that. If I gave you this and told you write it out in terms of cosine and sine, I would assume and dearly hope that practically all of you could do that. Unfortunately, when you want to use the formula, it's this way you want to use it, in the opposite direction. You're starting with this and want to convert it to that. Now, the proof, therefore, will not be of much help. It requires you to go in the backwards direction and match up coefficients. It's much better to go forwards. Now, there are 2 proofs that go forwards. There's the 1802 proof. Since I didn't teach most of you 1802, I can't be sure you had it. So I'll spend 1 minute giving it to you. What is the 1802 proof? It is the following picture. Picture. I think this requires deep colored chalk. This is going to be pretty heavy. All right. First of all, the A and the B are the given, so I'm going to put in that vector. So there is the vector whose sides are, whose components are A and B. I'll write it without the I and J, and just in this. I hope you had from Jerison that form for the vector. If you don't like that, write AI plus BJ, okay? Now, there's another vector lurking around. It's the vector, the unit vector, whose, I'll write it this way, U because it's a unit vector, and theta to indicate that its angle is theta. Now, the reason for doing that is because you see that the left-hand side is a dot product of 2 vectors. The left-hand side of the identity is the dot product of the vector AB with the vector whose components are cosine theta and sine theta. That's what I'm calling this unit vector. It's a unit vector because cosine squared plus sine squared is 1. Now, all this formula is saying that the scalar product, the dot product of those 2 vectors, can be evaluated, if you know their components, by the left-hand side of the formula. And if you don't know their components, it can be evaluated in another way, the geometric evaluation, which goes, what is it? It's the magnitude of one times the magnitude of the other times the cosine of the included angle. Now, what's the included angle? Well, theta is this angle from the horizontal to that unit vector. This is the angle phi is this angle from this picture here. And therefore, the included angle between u theta and my pink vector is theta minus phi. That's the formula. It comes from 2 ways of calculating the scalar product of the vector whose coefficients are A and B, and the unit vector whose components are cosine theta and sine theta. All right, well, You should, that was 1802. There must be an 1803 proof also. Yes. What's the 1803 proof? The 1803 proof uses complex numbers. It says, look, take the left side, instead of viewing it as the dot product of two vectors, there's another way. You can think of it as the part of the product of two complex numbers. So the 1803 argument, really the complex number argument, says, look, multiply together a minus bi and the complex number cosine theta plus I sine theta. There are different ways of explaining why I want to put the minus I there instead of I, but the simplest is because I want, when I take the real part, to get the left-hand side. I will. If I take the real part of this, I'm going to get a cosine theta plus b sine theta because of negative I and I make 1. Multiplied together. All right, that's the left-hand side. And now the right-hand side, I'm going to use polar representation instead. What's the polar representation of this guy? Well, if AB has the angle theta, then A negative B, A minus BI, goes down below. It has the angle minus phi. So this has magnitude in its polar representation. Its magnitude is a squared plus b squared, and its angle is negative phi, not positive phi, because of this. A minus bi goes below the axis if a and b are positive. So it's e to the minus I phi. That's the first guy. And how about the second guy? Well, the second guy is e to the I theta. So what's the product? It is a squared plus b squared, the square root, times e to the I times theta minus phi. And now, what do I want? The real part of this, and I want the real part of this. So let's just say, take the real parts of both sides. If I take the real part of the left-hand side, I get a cosine theta plus b sine theta. If I take the real part of this side, I get square root of a squared plus b squared times e times the cosine, that's the real part, right, of theta minus phi, which is just what it's supposed to be. Well, with 3 different arguments, I'm really pounding the table on this formula, but I think there's something to be learned from at least 2 of them. And, you know, I'm still, for a while, I'll never miss an opportunity to bang complex numbers into your head, you know, because in some sense you have to reproduce the experience of the race. As I mentioned in the notes, it took mathematicians 300 or 400 years to get used to complex numbers. So if it takes you 3 or 4 weeks, that's not too bad.